Hello everyone, we are live again. I hope that everyone can hear me. So am I audible? Is the video clear? I hope so. All right, so once again, we are going to cover quicksort today. So yesterday we were supposed to cover quicksort, but we had some internet issues, which is why the lecture for yesterday got postponed to today. All right. So we'll be doing a deep dive into quicksort. We'll be looking at the intuition behind it. We will be looking at the algorithm. We will be analyzing the time complexity of quicksort. And finally, we will be solving a couple of questions on quicksort. All right. Now, as always, after the lecture is over today, please make sure that you go and practice with the problem set. So the link to the problem set will be in the video description. Right. Go over there and practice the problems, because it is by practicing that you will finally internalize the concepts. Apart from that, there is a link to Scalar discussion chat also in the video description. So if you go over there, you will be able to find the lecture notes of all the previous lectures, today's lecture, and you will be able to interact with other peers who are taking this course along with you. All right. So Shivam mentions that there is some echo in my voice. Is that the case, guys? I guess not. All right. In that case, let us begin. Okay. So some of you already got introduced to the problem yesterday, but let me quickly repeat the problem once again. Okay. So let me just share my screen for you guys. All right. Can you all see the tablet? Can you all see what I'm writing over here? Yes. Perfect. All right. Let us begin. So the problem goes something like this: that you have n pens, right? And you have n different caps, right? So everyone understands what a pen is and what a cap for a pen is, right? Now these are kept on the table, right? And they are kind of mixed up, right? So there are n pens lying on the table, and there are n caps that are also lying on the table. Now what you are supposed to do is you are supposed to match these caps with the pens. So you are supposed to take the appropriate pen, you're supposed to take the appropriate cap, and you're supposed to put them together. All right. Today's topic is quicksort. So we will be building it via a problem first. Okay. Cool. So there are some constraints with this particular problem. So for example, let us suppose that you have a pen, right? This pen is going to have some fixed diameter, right? So this pen has some diameter d. All right. Now, if you're having a pen, then if a cap goes over this pen, right? If a particular cap goes over this pen, then this cap's internal diameter must also be d. Otherwise, this cap won't fit, right? So if the diameter of the cap is larger than the diameter of the pen, then the cap will be too loose, right? Alternatively, if the diameter of the cap is too small, then you won't be able to insert the pen into the cap, right? So we want to make sure that we pair up the correct pen with the correct cap. All right, that's the okay. Some people are saying that there is some still issue with audio, so just give me a second. I am going to check why we are. Is this better, guys? Am I audible now? Yes, no? Okay, I will assume that I am audible, or let me actually quickly check it out. Not seeing any responses in the chat over here. Am I audible, guys? Yes. Not seeing any responses in the chat over here. Okay, perfect. All right. I am audible. Okay. So now there is one further constraint, that if you have a pen, right? If you have a pen with a particular diameter, you can't really look at it and determine the exact diameter, right? Especially for a person like me who wears glasses, it is very difficult to look at a pen and know exactly what the diameter of that pen is. Similarly, if I look at a cap, I won't know what the diameter is. So I can't really compare two different pens. All right. So if I have this pen and I have another pen, I can't really tell by looking at it which pen is smaller or which pen is larger. Right? I cannot compare the diameters directly. All right.
Cool. So if that is the case, then how would you solve this particular problem? So I hope the problem is clear to everyone. We have n different pens, we have n different caps. You cannot really compare the diameters of different pens, and you cannot compare the diameters of different caps. You are supposed, they are all mixed up on the table, and you are supposed to pair them up. You're supposed to match the correct pen with the correct cap. All right, so let us think of some approach. All right, it is fine that we start with some sort of a brute force, some sort of a very naive approach. We don't have to think of the optimized solution upfront. All right, so let us think of some solution first of all. All right, so some of you are saying that we would try to sort them. All right, so okay, that is one reasonable answer. So what we could do is, let us say that there are some caps over here, right? And let us say that there are some pens over here. If I sort them in ascending order of diameter, then what will happen? What will happen then? Then the smallest cap will be here, the larger cap will be here, and the largest cap will be over here. Similarly, the smallest pen will be here, and the largest pen will be over here, and they will pair up one to one. Right? This smallest cap belongs to this smallest pen. This largest cap will belong to this largest pen. Right? That is supposed to be the case. But how exactly would you sort them? Right? Remember that for sorting, you will need to compare the caps. Right? If you're going to sort the caps, or if you're going to sort the pens, you will need to compare different pens, and you will need to compare different caps. How will you do that if you can't really tell which cap is larger or which cap is smaller by looking at the cap? Does that make sense? So this seems like a good approach. Sorting will definitely solve the problem, but we are not sure exactly how we will sort. Okay, so let us step back from this sorting approach. And think of a more naive, more brute force solution. Okay, so yes, is there any solution that comes to your mind? So we are looking for a naive or a simple solution that gets the job done. We won't worry about the complexity, but we want to get the job done. Okay, so Webber here suggests, Webber and Hussain over here also suggest that what we can do is we can try each pen with each cap, right? So what we can do is, suppose that there are n caps over here, and we also have n pens. Okay, we will take any arbitrary pen, right? We will pick one pen. We don't really care which pen it is, right? We will just pick one of the pens, and we will try this pen on each of the caps. Yes, can we do that? We can try this pen with each of the caps, and I mean, most of them will not match, but there will be one cap. There will be one cap somewhere with which this pen will match, right? Is that correct? So in how many steps did we find the correct cap for this particular pen? How many steps did it take for us to find the correct cap for this particular pen? There were n caps and there were n pens. It took us n steps. Right? It took us n steps. Why? Because we were comparing with each of the caps, and there are n caps, right? Okay, so the first pen and the first cap are sorted. This pen and this cap are sorted. Now what do I have? Now I have n minus 1 caps, and I have n minus 1 pens remaining. Yes, once I have paid up a pen with a cap, I will just put them aside. I won't put them back on the table, right? So now, once again, I will choose any pen and I will try it with all the caps. How many steps will this take now? It will take n minus 1 steps, right? Because there are n minus 1 caps remaining, right? Okay. So if we continue this way, we pick a pen, we try it with the remaining caps, and we set it aside. Then we pick another pen, we try with the remaining caps, we set it aside. Then how many steps are we taking in total? So for the first pen, we had to do n steps. For the second pen, we had to do n minus 1 steps. Third pen took n minus 2 steps, and so on. How much time will the last pen take? When there is just one pen and one cap remaining, how many steps will that take? It will just take one step, right? You pick up the pen, you pick up the cap, and you plug them in, right? So this will go all the way to 1. Okay. So can someone tell me what the summation of this particular thing is? This is 1 plus 2 all the way till n, right? This is the sum of first and natural numbers. Yes, this is also the same as n plus 1 C2. This is also called the nth triangular number, right? And what is the formula? Does anyone remember? No, it is not factorial. Factorial will happen when you multiply all of these things, right? For example, if you had this n times n minus 1 times n minus 2 all the way till 1, then this would be n factorial, right? But this is not multiplication. This is simply addition. The formula for this is equal to n times n plus 1 by 2, right? I hope that everyone remembers this, right? This is the sum of first and natural numbers. This is the sum. I goes from 1 to n of I, the first n natural numbers. Okay, so we understand that if we do this naive approach, then we are taking this much time, right? And how much time is this? This is order of n squared time. Is that correct? This naive approach takes order of n squared time. It is kind of slow, but it gets the job done, right? It gets the job done, and that is a good thing. Okay. Now let us try to optimize this. Okay, let us try to optimize this and see if we have any better ideas. Okay. So would anyone want to give a shot? So I see a couple of approaches in the chat. All right. So let us think what really happened. Right. Let us go back to this example. Suppose that there were n caps and there were n pens. We took one pen. Right. We took one pen and we tried it with all the different caps. Right. What did we gain out of this? What information did we get out of this? So the first piece of information that we got and that we used was this pen matched with which cap, right? There will be exactly one cap with which this pen will match, and we got that information. But is there anything else that we got out of this? Is there any other information that we got out of this? Yes, so Harshit has the right idea, right? Harshit has the right idea over here. Harshit says that, hey, when you are comparing, when you're trying to fit this pen over a particular cap, what you can try to see is which caps were smaller and which caps were larger. Yes, we could try to figure out which caps were smaller, which caps were larger. So suppose I compare it with this one, right? Let us say this was larger. What will I do? I will set this cap aside, right? I will set this cap aside in this part of the table. I will compare the next, I will compare with the next cap. Let us say that this was smaller, right? I will take this and I will put it over here. All right, and so on and so forth. I will compare with all the different caps. So what will I get? So my table will look like this. My table will look like this. I will have all the caps that were smaller. I will have all the caps that were larger. Right? These were the smaller caps. These were the larger caps. Apart from that, I will have the correct cap for this pen as well. Right? I will have the correct cap for this pen as well. Right? That is the entire information I get by doing these n steps. Right, by comparing that pen with all the caps. That is the information I get. Is that clear? First of all, is that clear? Right? That this is not the only information I get. I also get information about which caps are smaller and which caps are larger. Okay? Cool. Now, how can we utilize this information to improve the time complexity of our particular problem? So earlier the time complexity, when we were just using this information, was order of n squared. Now we would also like to use this information and see if somehow we can reduce the time complexity. Okay. Cool. So someone is saying that we can sort the caps and we can sort the pens and then we can easily pair them up. So once again, the problem says that you cannot really look at two pens and compare them. If you have two pens, you do not really know what their diameters are, right? And you can't. I mean, just by looking, you won't be able to tell which pen is bigger and which pen is smaller. The only way you can find the diameter of a particular pen is by trying to fit a cap on that pen. Okay, so we can't simply sort them. All right. But how do we judge larger caps and smaller caps? Well, that is easy, right? You pick this pen up. And you try this cap. If this cap is too loose, you know that the cap is larger, right? You will get to know if the cap is too loose or if the pen does not fit, then the cap is too tight. If you put the pen in and the cap falls out, then the cap is too loose. If you put the pen in and it just stays, then the cap is perfect, right? Does that make sense? Cool. Surit says there can be a lot of caps. How can we exactly say larger cap or smaller caps? Okay, once again, let us say that there are several caps over here, right? There are several caps of various sizes over here. Now, it might be that there are two caps which have very similar size. Right? This cap and this cap, they have very similar sizes. And by looking at them, I can't really tell which is larger or which is smaller. Right? My eyesight is not that good. But if I have a pen, let us suppose that if I have a pen, what I can do is I can try this pen, I can try fitting this pen in this cap, right? Suppose it fits. Suppose it fits. I also try fitting this pen in this cap. Suppose this cap is loose. Now can I tell which cap is bigger? Now can I tell which cap is bigger? Yes, I can tell that, okay, this cap is bigger, right? Because I know that, okay, this pen fits in this cap but does not fit in this cap. All right, cool. So what we are essentially saying is, when we have this pen, let us compare this pen with all the caps. Let us try to fit all the caps. There will be some cap. Let us say this cap that perfectly matches this pen. But for the other caps, some of them will be too tight and some of them will be too loose. Right? These will be too loose. Right? And based on that, we can segregate them. We can say, okay, let us put the smaller caps on one side, let us put the larger caps on one side, and let us keep the perfect pen and the perfect cap aside. We can take them off the table. All right? Cool. Let us see how we can utilize this information further. Okay. So, firstly, what we did was we took this set of caps, right? And we had one pen out of all the different n pens, right? And using this one pen in n steps, what did we do? We split these caps into smaller, larger, right? And the perfect cap. So there was one perfect cap over here as well. Okay. Now what can we do? Using this perfect cap. So we know that this pen fits this cap, right? And we have divided the caps, but we will also need to divide the pens. Right? We will also need to divide the pens. So let us do one more thing. Let us now take this perfect cap, right? And let us now try it with all the different pens. Okay. So we first tried the pen with the caps. We found the perfect cap. Then we tried the perfect cap with all the different pens. What will that give us? That will take once again, that will take n steps. Yes, that will take once again n steps. But what will that give us? That will once again allow us to divide the pens into smaller pens and larger pens. Is this clear? Is this clear? Yes or no? Would you like me to go through a concrete example? Let us go through a concrete example. Let us suppose that we have several caps: cap of diameter 1, cap of diameter 3, cap of diameter 4, cap of diameter 0, cap of diameter 8. Okay. And similarly, I have pens. So I have pen of diameter 0, pen of diameter 8, pen of diameter 1, pen diameter 3, pen diameter 4. Right? And they are mixed up. So what I will do is I will take any pen. So let us suppose I took this pen. Or let us suppose I took a different pen. Let us suppose that I took this pen. All right. Now what will I do with this pen? I will compare it with all the different caps. Now once I compare it with all the different caps, what will I get to know? I will get to know that C1 was smaller, C0 was smaller, right? C4 was too loose, C8 was too loose, and C3 fit perfectly. Right? C3 fit perfectly. This information, this segregation, it took me n steps. Now what I can do is, now I can take this C3 cap. Now I can take this C3 cap and compare it with all the different pens. Right? I can compare this C3 cap with all the different pens. And what will that give us? What will that give us? That will be able to tell me that, hey, C3 matches with P3, but P1, P0 was smaller than C3. Right? P1 was smaller than C3. P8 was larger than C3 and P4 was larger than C3. Right? Does that make sense? Notice that I have just paired one of them. Right? I was just able to make one correct selection, but my groups are now divided. The smaller pens in the smaller caps are here. The larger pens and the larger caps are here. Right? There is no one-to-one correspondence between. Oh, there is. I mean, I can't really say that. Okay, this goes with this. Right? They are still mixed up. The pens and caps over here, they are still mixed up. But at least I have segregated them into smaller caps and larger caps. Is that clear? Right? Cool. So this is the basic idea behind quicksort. All right. So let us see how this exactly helps us. Let us see how this helps us. So suppose that in the first step. In the first iteration, what did I do? I took a pen, I used n steps plus n steps, right? I used 2 n steps, and that allowed me to split. That allowed me to split my group into two parts. Right? Let us suppose that the size of these parts is roughly half. Okay, let us suppose that the size of this parts is roughly half. That is an assumption that we are making, but let us say that that is the case over here. All right. So basically, we are saying that let us suppose if we had n pens initially, let us suppose that there are n minus 1 by 2 pens which are smaller. Right. There are n minus 1 by 2 pens which are larger. Right. We have split them into 2 groups. Okay. Cool. So this was the first step. What will we do in the second step? Let us see what we will do in the second step. Now, in the second step, if there is a pen over here, should we compare this pen with any of these caps? Does it make sense? Does it make sense to compare this pen with any of the caps that were larger? Does it make sense? No, it does not, right? Because we already know that this pen was smaller than the previous pen, right? This pen was smaller than the first pen. And all these caps are larger than the first pen. So we should not compare this, right? Which means that now, if we take this pen, we will only have to compare it with these many different caps, right? Earlier, we had to compare it with all n different caps. Now we only have to compare it with n by 2 different caps. Do you see that? Now our decision group has become much smaller. The size of it has been halved. It has been reduced to half the original size. Yes? Does that make sense? Yes, we should only be comparing within the group because there's no point comparing it outside in the larger group, right? There's no point comparing a smaller pen with a larger cap. I know that they are not going to match. Okay? Cool. But I need to do this for both the groups. Remember, I need to do this for both the groups. I need to take a pen in this group and compare it within the group. Right? Similarly, I need to take a pen in this group and compare it within the group. Right? So I have 2 tasks now. Earlier, I was just taking 1 pen. Now I have 2 tasks. So in the second step, what will I do? I will do this n by 2 step plus n by 2 step for this particular group, for the smaller group. Right? Similarly, I will do n by 2 step plus n by 2 step for the larger group. Does that make sense? Yes? Yes, so I'm currently ignoring the minus 1 as a constant, right? It is not going to have much effect. So I'm just currently ignoring the minus 1 as a constant, all right? So I'm saying approximately n by 2 pens. Okay, cool. So if we continue this way, what do we now have after the second step? We have 4 different partitions, right? We started with 1 partition, we started with 1 group, then we had 2 groups, then we split them further into 4 different groups. And if we continue this way, we will keep on dividing further and further. Right? We will keep on dividing further and further. What will happen at the last? So suppose that there is one group over here which has just 1 pen and 1 cap. Right? I kept dividing them, and now only 1 pen and 1 cap are remaining. Okay. Now, do I need to divide that further? If there is 1 cap on the table and 1 pen on the table, do I need to do any sort of analysis to figure out, if they are matching? No, right? I know that they must match. Yes or no? Yes, so we only need to divide till 1 pen and 1 cap are remaining. So when each of these things will terminate when there is 1 pen and 1 cap remaining. Right? And then we don't need to divide it further. All right. So this is the basic intuition behind quicksort. This is how we will be able to match different pairs and different pens. Now, it doesn't really seem like a sort, right? It doesn't really seem like a sort so far. So far, we have only been matching pens and caps, right? So this is like a quick match, not a quick sort. We will try to generalize this into a quick sort. Okay, we will try to generalize this into a quick sort. But first of all, let us look at the pseudocode for this, right? Let us look at the pseudocode for this. So suppose that we were supposed to match pens, right? Let me call this the quick match algorithm. Quick match algorithm. All right. In this quick match algorithm, we had several pens and we had several caps. Okay. So this is the function quick match. We are getting several pens as input. So this will be a vector or a list or an array, whatever you can call it. Similarly, this will be a vector, right? Both of size n. All right. So what is the first step that I need to do? What is the first step that I need to do? I need to choose a pen. So pick a pen. Pick any pen. Right? What do I do with this pen? I compare it with all the different caps. With all the caps. Right? While comparing, I will segregate the caps. Right? Split the caps. Split the caps into smaller and larger. Right? Then what do we have to do? We also have to identify the correct cap. Right? In the same step, we can identify the correct cap. Okay. Now, what do we do? So can someone tell me quickly, what should we do now? So we have not done it, right? So we have to split the pens as well. Right? We have to split the pens as well. So now that we have this correct cap, using correct cap, split the pens as well. The pens as well. Right? Okay. Now, after all this is done, we have two groups. We have two groups. Right? We have three groups, in fact. One group is of the smaller pens and caps. Right? Then there is this pen and its corresponding cap. And I have the larger pens and the caps. Right? This is what I have. Yes? Okay, so what am I going to do with this? I'm going to take this off from the table. So this is already done. So these gets removed from the table. Remove from table. Right? I'll remove them from my table. What about the other two? What about the other two? I will repeat this procedure. Right? I will repeat this procedure for the other two things. So basically, how do I repeat this procedure? I call this recursively. So I will say quick match of the smaller pens and smaller caps, right? And once again, I will do a quick match of the larger pens and larger caps. Is that clear? Right? What is the purpose of splitting again using the cap? Okay. So let us say that I have this pen, and using this pen, I can say what these are the smaller caps, these are the larger caps, right? But I don't really know which the smaller pens and larger pens are, right? I need to make sure that these smaller caps are compared only with the smaller pens, right? I don't want to compare the smaller caps with the larger pens. So I need to split the pens as well, right? That is the purpose. Is that clear? Yes. Harsh, your question is very nice. So Harsh has asked the question, what if the chosen pen is minimum or maximum, right? That will lead to some issues. Okay, Harsh. So we will look at those issues when we analyze the time complexity of the algorithm. Right? That's a good question. Just keep that in mind. Okay, we will come to that. All right. Okay. So if we do this, we will be able to match all the different pens and all different caps. All right. Is this clear? Is this clear? Perfect. Now, this was for the matching thing. Right? This was for the matching thing. Let us quickly look at the quicksort algorithm. This was basically to build the intuition of quicksort. Okay. Now we were not really sorting over here. We were matching pens and caps. But let us see how we can use this to sort different numbers. Okay. Let us quickly see that. Okay. So how does quicksort work? So quicksort works in a very, very similar way. Right? Quicksort works in a very, very similar way. Let us suppose that I now have an array of n numbers, right? Integers, let us say. Okay, so I have this array It goes from 0, 1, all the way till n minus 1. So there are n integers, and the integers have some values. So 3, 7, minus 1, 0, 6, 8, and something like this. Right? There are some integers. And I want to sort them. Right? Now, how can I apply quicksort for this particular question? Right? How can I apply quicksort to sort this particular array? All right. So what quicksort says, very similarly, now you will be able to see the similarity. Right? What quicksort says is, let us suppose that you are supposed to sort this array. Okay, let us suppose that you are supposed to sort this array. Then first of all, let us pick any element. Pick any element. Right? Pick any element whatsoever. Let us call this element the pivot. All right. So, for example, let us suppose that we picked this element, perhaps. Right. Let us say that we picked 3. Okay, and we will call this the pivot. In the second step, what we will do is we will partition this array. Partition the array using pivot. All right. So what does partition mean? Partition means to split it into smaller and larger group. Right. So what we will do is we will take this particular 3 element and we'll compare it with all the other elements. Right. We will compare it with all the elements. So what about 7? So we have a smaller group. Right. We have a larger group. Where should 7 go? Is 7 smaller than 3 or larger than 3? It is larger than 3. Right. So 7 will go into this group. 7. What about minus 1? Minus 1 is smaller. So minus 1 will go over here. What about 0? 0 is smaller. 0 goes over here. 6 is larger. 8 is larger. Right? This is what happens. Is that clear? Right. So after partitioning, we will have 2 things. So after partitioning, this will give us 2 things. This will give us the smaller set, and this will give us the larger set. All right. Now what can we do? What can we do? We can sort the smaller set separately. Smaller set. Right? We can sort the larger set separately. Yes. Let us call this left. Let us call this left. And let us call this right. Okay. So what we are supposed to return? We wanted the complete sorted arrangement. So we just return left, right? We put the left part, then we put the pivot, then we put the right part. Yes. So this is not exactly code. This is just pseudo code. But is this approach clear? So this is how quicksort works. This is quicksort. Is this clear? So given an array, we pick any element and we call it the pivot. Right? We pick any element and we call it the pivot. Using this pivot, we partition the array into 2 parts, the smaller set and the larger set. Right? Then we recursion, right? Recursion. We recursively call the sort on the smaller set separately and on the larger set separately. Right? So that will sort the smaller set, that will sort the larger set. Okay. And finally, we will simply merge them together. We will say that, okay, let us take the left sorted part, let's put the pivot in middle, let's take the right sorted part, and we are done. Okay. All right. Now, those of you who are familiar with recursion, you can spot a problem over here. Right? You can spot a problem over here. This recursion is infinite. This recursion never stops. Right? This recursion never stops. So to make this recursion stop, I have to do something else. I have to include a base case. Right? So let me quickly include the base case over here. Any element. So what I will say is, if array has only one element, right? Then I can just return the array itself. I don't need to do anything. Yes. So this is the base case. Right? And now with this, we have the quicksort algorithm complete. Is that clear? Any doubt so far? So do not worry about the time complexity for now. Okay, do not worry about the time complexity for now. Is the approach clear? Is the algorithm clear? Yes? Yes, no? Okay, cool. So Srinivas, do not worry about the time complexity for now. We will come to the time complexity in 1 minute. Okay. First, let us go through the pseudocode and then we will come to the time complexity. Okay, perfect. Cool. Now, how would you really partition? So you understand choosing an element, right? You can choose an element. Can you write the code for that? Can you write the code for choosing an element? Yes, so certainly you can, right? Choosing an element, this pivot thing, my bad, right? Then how will you write the code for partitioning it? How will you write the code for partitioning it? So what you can do is you can create two new arrays and you can compare each and every element. So if this element is smaller, put this in the left array. If this element is larger, put it in the right array. Yes, you can do that. Cool. So let us actually, so this was pseudocode, right? Let us try to write some actual code for this. Okay, let us try to write some actual code for this. There's a lot of different things. There's a lot of different variants that we are going to look at. Okay, so we have quicksort, right? And in this quicksort, so I'm going to use a Python-like syntax. All right, I'm going to use the Python-like syntax because it is very close to pseudocode. All right, so do not worry if you are coming from C++ or Java or Go or Rust. Do not really worry about that. You will be able to understand what is happening. Okay, so let us say that I have this array over here. Right, I have this array over here. So how will quicksort work? Quicksort will say pivot equals to choose some element. So what element would you like to choose? What element would you like to choose? So let us just choose the first element, right? We are not really sure what element to choose. We will look at how to choose an element later on. Okay, for now, let us choose the first element itself. Okay. Then what will we do? We will say smaller, comma larger equals to partition this array using this pivot. Right? So this partition is a function that we will write. Okay, so over here we will write the partition function as well. So we will write the partition function. This will take an array, right? It will take a pivot and it will return us two arrays. It is supposed to return two arrays. Okay, we will write this later on. Okay, cool. So once we have this smaller and larger, what are we supposed to do? We are supposed to quicksort the smaller, quicksort the larger, right? And then return smaller plus pivot plus larger, right? This is array concatenation. This is array concatenation in Java, in Python, list concatenation. Okay, does that make sense? And I just have to carefully include my base case. So if the length of AR equals to 1, then simply return AR. Is that here? Now that was pseudocode. This is the actual code that will run. But we still have to do the partition part. Right? We still have to do the partition part. The reason I am doing this in so much detail is because there's a lot of variety that you can, there's a lot of decisions that you can make. And based on those decisions, the time complexity of your algorithm and the space complexity of your algorithm will change. Right? Is that clear? Cool. So let us look at this partition algorithm. So how can we partition this? Let us say that we create a smaller array, which is initially empty. Let us create a larger array, which is also initially empty. Okay. Then what we will do is we will say for every element, every item in my array, I will compare it with the pivot. So if item is smaller than pivot, then what will I do? I will put it in the smaller part. I will say smaller dot append item, right? On the other hand, if it is greater, if item is greater than the pivot, right? Then, or let us say this, let us make this less than or equal to. So let us make this actually less than or equal to, right? And let us make this greater. So if it is greater than the pivot, I will say larger dot append item. Okay, and then I simply return both these arrays. So I simply return smaller and I also return larger. All right. So this is the entire algorithm. This is the partition algorithm and this is the quicksort algorithm. This completely is called quicksort. What about the next iteration? So the next iteration is happening in this particular thing, right? This is recursion. Okay, so this is where the next iteration is happening. Is that clear or no? So once we split it into smaller and larger, we will recursively call the same quicksort function over those new arrays. Okay, we got a smaller array. Let me quicksort the smaller array. Right? How will I quicksort the smaller array? I don't have to worry about that because I'm literally defining the quicksort algorithm. Is that clear or not? That is how recursion works. You define a problem in terms of smaller problems. Is that clear? Perfect. So this is the algorithm. Any doubts so far? Before we continue, any doubts so far? All right, it doesn't seem that there are doubts. Okay. Now let us try. Any conditions to select the pivot element? Vijay, we will come to that. Vijay side, we will come to how to select the pivot in some time. Okay, cool. Now that we have this, let us try to analyze this algorithm. Analyze this algorithm. Right? We will analyze both the time complexity and we will analyze the space complexity. Okay. Kanta says, how do we implement this algorithm in competitive coding problems? So Kanta, you will have to do that, right? So this lecture is to build the intuition. This lecture is to give you the pseudocode, right? This is not pseudocode. This code will actually work. This is Python code that will actually work. Right? If you are using some other language, you will have to try to implement in that language. Okay. Now the point is that after this lecture is over, there will be a link. I mean, there is a link in the video description that has a set of problems that you can try. So if you go over there and you try those problems out, that will give you the experience of actually implementing this in competitive programming. All right. This will give you the experience of actually implementing this in competitive programming. Okay. Return value not handled, right? My bad. Return value not handled, right? So basically, this says that this smaller equals to quicksort of smaller and larger equals to quicksort of larger. Okay, and then we are concatenating it. Smaller than pivot, then larger. All right, Himanshu? Cool. Thank you for pointing that out. Okay, now let us analyze the time and space complexity. So over here, several of you had pointed out what really happens with different pivots. Right? What really happens with different pivots. So let us take an example. Let us say that we have numbers something like this: -1, 0, 3, 4, 6, 2, 8. Okay, let us say that this is our particular array. So let us choose some pivot. Let us say that initially 3 is the pivot. Okay, initially 3 is the pivot. Using 3, we will split this up. So how will the split up look like? So we will have -1, we will have 0, then we will have 2, right? Over here, we will have 3. And on the right, what will we have? We will have 4, we will have 6, we will have 8. Is that clear? Yes, let us suppose that initially we chose this pivot. Then this will be the split, right? Similarly, let us try to do this once again. So over here, let us say that we chose this as the pivot. Right? Let us say that we chose this as the pivot. So what will happen? We will get -1 over here. We will get 0 in the middle. We will get 2 over here. Similarly, let us say we chose this as the pivot. Right? What will we get? We will get 4, 6 in the middle, and 8 on the right. Okay. And since now these are single elements. These are single element arrays. I don't need to split this further. Right? I can just return from here. Yes, I can just return from here. Is that clear? Right? So this is the good case. Let us see what the time complexity of this good case is. So this is the good case. What is the good case? The good case is when the pivot divides the array into halves, right? Into approximately equal halves. All right, into approximately equal halves. So we started with n elements. Right? After the first step, we have 2 new arrays of size n by 2 and n by 2 approximately. Right? This might be -1 + 1, but approximately n by 2. Is that clear? That is the good case. We chose a good pivot that divides the array into 2 almost equal parts. Is that clear? Yes. For this division, to do this division, how many steps did we take? Right? This division did not come for free, right? This partition algorithm, it took some time. How much time did the partition algorithm take? If I call the partition algorithm on an array of size n, then how many steps will the partition algorithm take? It will take n steps. Right? It will take n steps. Because the partition algorithm is a simple loop, right? The partition algorithm simply loops over all the items in the array and then inserts them into some of the smaller or the larger array. So this will take n steps. Cool. So basically what happened was I started with a problem of size n. Right? I started with a problem of size n. This is the notation. This is the notation. This is saying the time complexity, time to solve problem of size n. Okay, this Tn is the time to solve a problem of size n. So what will I do? I will spend n steps for the partition algorithm. After doing this n steps, what will I have? I will have two sets now, right? I will have two sets. I will have a set of n by 2 and I will have another set of n by 2. And I need to sort these sets. How much time does it take to sort a set of n by 2? So Tn is the time it takes to sort n elements. So how much time does it take to sort n by 2 elements? Well, Tn by 2, right? So basically what I'm saying is, once I have spent this n time doing the partition, then I will have to solve this subproblem and I will have to solve this subproblem. Does that make sense? This was the smaller set and this was the larger set. I will have to solve two new subproblems. Okay? So this thing is called a recurrence relation. Recurrence relation. All right, and there's a lot of different ways that you can solve this recurrence relation. You can solve this using something called the master method, right? Or you can solve this by repeated substitution. Right? There are a lot of different ways of solving this recurrence relation. We will not be going over how to solve this recurrence today. Okay, we will have a different class that will explain how to solve different recurrence relationships. Okay. For now, I'm just going to tell you the result of this. Okay. For now, I'm just going to tell you the result of this. You can verify that with the master method if you are aware of that. Okay. So Tn, if you solve this equation, you will find that Tn comes out to actually n log n base 2. Is that clear? Yes. So Tn comes out to be n log n base 2. That tells us that the time complexity of quicksort, right? In the good case, so remember, this is the good case. In this case, the pivot always divides the array into equal halves, right? In the good case, is order of n log n. Is that clear? Yes, is that clear? Cool. Now let us also look at the bad case. So a lot of you pointed out that, okay, let us say that we have this particular array, right? 0, -1, 0, 3, 7, 2, 1, 6. Okay, let us say that this is the array. What if we happen to choose this as the pivot? That can totally happen, right? In fact, in our code, we chose the first element as the pivot, right? Remember? So when we wrote this code, we said that pivot equals to AR of 0. So what really happens when we choose a bad pivot? So what will happen in this case? How will this divide the array? So we will have the smaller set over here. Is there anything that is smaller than -1? In this particular array, is there any number that is smaller than -1? No, it is not. Right? So this will be empty. There are 0 elements over here. Then -1 will be sitting in the middle. Then we will have all the larger elements. What all larger elements will we have? We will have 0, we will have 3, right? We will have 3, then 7, then 2, then 1, then 6. Okay, let us go further. So this doesn't have any elements, so I don't need to do anything with this. This doesn't have any elements, so I don't really need to do anything with this. Let us work with the right array. Okay, so once again, let us say that I chose this 0 as the pivot. Right? I chose 0 as the pivot. So what will happen? Once again, the smaller set will be empty. I will have 0 and I will have 3, 7, 2, 1, and 6. Okay. Now let us do it once again. Let us choose 3 as the pivot now. Okay, we are always choosing the first element. Right? Or let us make it even worse. Let us now choose 1 as the pivot. Right? So what will happen now? We will further split this into nothing, then 1, then 3, 7, 2, 6. right? Once again, let us choose 2 as a pivot, and so on and so forth, right? Nothing over here, 2 over here, right? And we will have what? We will have 3, 7, 6, and so on and so forth. So do you see what is happening over here? Do you see what is happening over here? This is the same as the brute force approach. This is the same as the brute force approach. When this was my pivot, I compared it with everything. Right? I compared it with everything. Now this is my pivot. So this was n comparisons. Now this is my pivot. Now I compare this with everything else. This is n minus 1 comparisons. Now I compare this with everything else. This is n minus 2 comparisons, and so on. Right? So because I chose a bad pivot, because the splitting of the array is not good, it can happen that quicksort can take order of n square time. Right? If the pivot happens to be bad, right? If this happens to be a skewed case, a bad pivot, then quicksort can take order of n square time. Is that clear to everyone? Is that clear to everyone? Yes. So the time complexity of quicksort, right? Quicksort is what? In the best case, it is order of n log n. In the worst case, it is order of n square, right? And what really happens in practice, in average or in practice, right? Now, average does not really, so the average case has a mathematical definition, right? Average does not mean in practice, right? Average has a mathematical definition. We calculate the time over a certain number of operations, right? Over a given pattern of input. But let us consider that we are talking about in practice. What really happens in practice? Okay. In practice, this turns out to be order of n log n. Right? Just remember that whenever you code quicksort algorithm, most of the time it will take n log n time. However, if you are unlucky, if you happen to be unlucky, if the input is in a particular arrangement, then your algorithm can also take n square time. Right? If you happen to be unlucky. Is that clear? Yes, everyone, we will figure out how to choose the best pivot in some time. Okay, let us first discuss the complexity of it. Then we will see how to choose the best pivot. All right, is this part clear to everyone? Perfect. So this is the time complexity of quicksort. Now let us come to the space complexity. Right? We care about space complexity as well. Okay. So what about the space complexity of quicksort? What about the space complexity of quicksort? Well, that depends on how we choose to partition the array, right? How we choose to partition the array. So over here in my pseudocode, what have we done? We have said something like this. The partition array, it creates two new arrays, right? It creates two new arrays of size n by 2 and n by 2. So overall, every time I do a partition, it will take order of n space extra. Right? Every time I do a partition, it will take order of n space extra. Does that make sense? Yes. What is the space complexity? The space complexity is the amount of space your algorithm takes, right, for a given input. So just like time complexity talks about how many operations did it take, how much time did it take. Space complexity talks about how much memory did you use, right? How much memory did you use? So why is space complexity necessary? What really happens is, a lot of the times, for example, let us say that you are running this algorithm on your watch, right? So people now have smartwatches, right? People now have eye implants, right? So if you're trying to, or people have pacemakers in their hearts, right? If you're trying to run an algorithm on a pacemaker, the pacemaker does not have 2 gigabytes of RAM, right? Your watch does not have 2 gigabytes of RAM. It has very little memory. So it could be the case that you are willing to sacrifice time complexity. Right? You're willing to say that, okay, it is okay if it takes a little more time. I want to optimize the memory usage. Okay, which is why we also study the space complexity of algorithms. All right. So if this is my partition algorithm, then what will happen? Now, once again, let us consider both the cases. So let us consider what happens in the good case. In the good case, I have this array. I split it into 2 parts. Right? This is of size n. This is size n by 2, n by 2. I split this further, n by 4, n by 4, n by 4, n by 4, all the way till each of them have size 1, right? Till each of them have size 1. Okay. So how much space am I really using over here? How much space am I really using over here? So remember that even though that we are doing recursion, when I make the split, right? When I go from this step to this step, I will have to store both these arrays in the memory. Right? I will have to store left and right, both the arrays in the memory. I cannot simply drop one because I have to recurse on that as well later. Right? So I have to store both of them in the memory. Okay. So over here, I had an array of size n. At this particular level also, I have total n memory that I'm using. Right? I total have n memory that I'm using. Over here as well, how much memory am I using? N by 4 plus n by 4 plus n by 4 plus n by 4, which is once again n. Right? And so on and so forth. Even at the last level, every element is separate. Right? Every element stands alone and there are n elements. So this will be n memory usage here as well. Right? So how much memory am I really using in this case? How much memory am I really using in this case? So that depends on how many times this n occurs, right? How many times this n occurs? What is the height? What is the height of this tree? Right? Or basically, how many times do I have to split? Right? Now, if my partition is good, if it is a good case, if I'm splitting it into halves every time, then the number of steps it will take will be log n. Right? Will be log n. And at every step, I'm taking n memory. So my total space will be order of n log n. Is that clear? Yes. Cool. Now you can also see that if this is the bad case, if my partition is not good, then the space will very easily become order of n square. Right? My space will become order of n square because I will be using order of n, and I will my depth. I will have to do the splitting n different times. So this will become order of n square space. Is that clear? Cool. So just remember that for this particular partition algorithm, that I used over there, the space complexity in the best case space complexity is order of n log n, and the worst case space complexity is order of n square. Okay. The question now is, could we try a different partition algorithm? Right? Could we try to make the partition algorithm in place? Right? Can we make the partition in place? What does in place mean? In place means without allocating any extra memory. Okay, without allocating any extra memory. It turns out you can. Right? So normally, when you will be coding quicksort, you won't code it like the way I have told you above. Right? You will code it something like this. So you will say quicksort of an array. You will have the start and you will have the end. Okay, you will have the start and you will have the end. Then what you will say is you will check first of all if start is equal to n minus 1. That means that there is just one element. Right? That means that there is just one element. In this case, I will just return the array. Right? So let me keep it at Python syntax. In this particular case, I will just return the array itself. Right? Otherwise, what will I do? Otherwise, I will say that index equals to partition my array from start till end. Right? I'm going to code a different partition algorithm over here. I'm going to use a partition algorithm that is in place, that does not use any extra memory. All right. Cool. So once I have this index, what will I do? I will say quicksort the array from start till index minus 1. Okay. Similarly, quicksort the array from index plus 1 till the end. Right? And once we are done, so over here we are not allocating any extra memory. We are not creating any new arrays. So we don't need to concatenate the arrays at the end. Right? We don't need to concatenate the arrays at the end. This partition algorithm will move the elements inside the array itself. Right? So once I'm done over here, once I'm done with these two steps, I don't need to do anything else. I can simply return from here. Right? I can simply return this array itself because this array would have been sorted already. Is that clear? Yes or no? Now we will talk about how this partition algorithm works. We will talk about how this partition algorithm works. But is this clear that I can code the partition algorithm in an in-place manner without using extra memory? And if I do that, I will have to introduce some extra parameters. I will have to introduce the start and end because I will have to keep track of what part of the array I'm talking about, right? What group I'm talking about. Is that clear? Yes? Okay. Now let us see how this partition algorithm can work in place, right? How this partition algorithm can work in place. So let us do it with an example first. Let us do it with an example first. Let us say that once again we have -1, 0, 3, 6, 2, 1, 8. All right. And let us say that we choose this as the pivot. Or let us say that we have one more element over here. Let us add a 4 over here. Okay. Let us say that this is our pivot. Okay, let us say that this is a pivot. Now what I can do is I can start from the left. I can start from the left and I can try comparing every element with this pivot. Okay, I can try comparing every element with this pivot. So initially I have -1. Is -1 smaller than 4 or larger than 4? It is smaller than 4, right? So I will not do anything. I will simply increment this. I will move my pointer ahead. Okay, I will move my pointer ahead. Now once again, is 0 smaller than 4 or larger than 4? It is smaller. So I will move my pointer ahead. Okay. Now 3 is still smaller. So I'll move my pointer ahead. Okay. Now I am at 6. 6 is larger than 4. Right? 6 is larger than 4. So what I need to do is I need to swap this 6 with something. Right? I don't want the 6 over here. I don't want the 6 over here. I want the 6 in the larger set. I want the 6 over at the right. Yes. So what I will do is I will mark its position. I will mark its position. I will remember its positions and I will continue forward. I will continue forward. When I come to 2, I will swap this 2 with this 6. Okay, I will swap this 2 with this 6. So what will happen is this 2 will come over here. This 6 will come over here. Okay. Then I will come to 1. 1 is still smaller than 4. So I will swap the 6 with 1. Okay, I will swap the 6 with 1. So 1 will come over here. 6 will come over here. All right. Then I will go to 8. 8 is larger than 4. Right? 8 is larger than 4. So I won't do anything. I will continue forward. And I reach the end. When I reach the end, what do I do? When I reach the end, what do I do? I swap this 4 with this 6. Okay, I swap this 4 with this 6. So what will happen over here? 4 will come over here. And 6 will come over here. Right? So what essentially happened? This array is now correctly partitioned around this 4. Right? This 4 was the pivot. Right? And now notice that everything on the left is smaller and everything on the right is larger. Yes or no? Yes. So there are several ways that you can implement this partition algorithm. This is one of the ways. Right? This, what I'm showing you, is one of the ways of doing it in place. Okay, without using any extra memory. And notice over here that we did not use any extra memory. Right? I mean, if we use extra memory, but that was constant memory. We did not use any extra memory. Okay. So let us quickly write the pseudocode for this. So I have partition, I have an array, and I have a start and I have an end. Right? I need to partition this array. So first of all, what will I do is I will choose the pivot. Right? I will say pivot equals to AR of end. I will choose the last element as the pivot. Right? The last element, which was 4 initially, as the pivot. Then what will I say? I will have a index. Index equals to start. What this index signifies is which element should I swap a current element with. Right? This index, this remembers what was the last position of a smaller element. Okay, this is what this remembers. Okay. Now what will I do? I will make a loop. So I will say for current will go from start till end -1. Okay, so current will go over all the different elements. Okay, Then what will I do? I will compare this A of current. I will compare this AR of current. AR of current. What should I compare this with? I'm comparing this with the pivot. Right? Pivot is what I want to base my calculations on. So I will check if this is lesser than the pivot. If this is lesser than the pivot, then it is perfectly fine. Right? If it is lesser than the pivot, then I don't need to do anything. I can simply if this is lesser than the pivot, then what I need to do is I need to swap. I need to swap what? I need to swap A of index, AR of index with AR of current. Okay, AR of index with AR of current, and I can do index plus 1. Index plus equals to 1. All right. Once I'm done with this entire thing, I can simply swap AR of index with this pivot, with AR of n. Basically, AR of pivot, comma AR of n. So AR of n had my pivot, right? And then I can simply return the index. Okay. So this pseudocode is doing exactly what we discussed over here, right? If we have time, we can also try to dry run it, but I guess we are over time already. So I'm not sure if we will be able to dry run it today. But if you come into the discussion group, I will be able to explain it much better to you. Okay. So basically, this pseudocode, this code is doing exactly the same thing what we discussed over here. And so what it will do is it will choose the last element. It will find its correct position. It will partition the array around this pivot, right? And it will return what the correct position of that pivot was. It will return that index, and we will use this index further in this particular location, right? So we are getting this index over here, and we are calling quicksort again recursively based on this index. All right. So Rahul, once again, if the array is sorted, so notice that this partition algorithm is just in place. It is not using any extra space, right? It does not really improve the pivot. It could still happen that the pivot is good or the pivot is bad, right? If the array is sorted, then the pivot will always be bad. All right, Rahul. So this is just an in-place partition algorithm. This does not have anything to do with the pivot. It is just choosing an arbitrary pivot. It's just choosing the last element as the pivot. Okay. So if I have this, then what is the time complexity? So earlier, my partition algorithm was not in place. It was allocating extra space, right? And the time complexity and the space complexities were order of n log n and order of n square. Right? This was the space complexities in the good and bad case. Right? Now that my partition algorithm is in place, it does not use any extra space. Now, what do you think the space complexity will be? If my partition algorithm does not use any extra space, what do you think will my space complexity be? Well, the space complexity should be just order of 1, right? I'm not using any extra space. Right? If I'm not using any extra space, the space complexity should be order of 1, but not so fast, right? Not so fast. This is not correct, because there is also this recursion stack that I have to consider, right? I am doing recursion. Recursion has some space complexity. I cannot simply ignore that space complexity, right? So does everyone remember? Recursion uses a stack internally, right? And recursion stack, I have to tell the complexity of recursion stack as well, right? So let us quickly see. So I had an array over here of size n. Okay. What did I do? I called partition that did not use any extra memory. After partition, I have this same array. Right? I have the same array. This array has not changed. I'm just manipulating the indexes. Right? I'm not creating a new array over here. Right? Then I will split it further. Once again, I'm using the same array. I'm not creating a new array. Right? And so on and so forth. Right? So on and so forth. Right? Finally, I will have the array which will be sorted. This array will be sorted. So this is happening. This is what is happening in this particular partition algorithm. Now, what is the space complexity over here? So I had n space which was given to me. Right? I'm modifying things internally. Right? I'm not allocating new space. So what is the space complexity? The space complexity will be determined by the recursion stack. basically how deep is this tree, right? What is the depth of this tree, right? So what is the depth of this tree currently? What is the depth of this tree? Well, that depends on the pivot, right? That depends if we have good pivot or if we had bad pivot, right? If we have good pivot or if we have bad pivot. If we have good pivot, then this will take log of n space, right? Order of log n space. If we had bad pivot, then it will take order of n space. Does that make sense? Because the space will depend on the recursion depth, right? So if we have good pivot, then it will take only log n space. If we had bad pivot, it will take order of n space. So no, it will not take order of n log n space. No, it will not take order of n log n space because of this partition algorithm. This partition algorithm is in place. It does not allocate any extra memory. So the only memory that you are allocating is for the recursion stack. Okay, it's for the recursion stack. And if your pivot is good, then the recursion stack will only have log n elements at maximum. Is that clear? Yes. So let me quickly recap. Quick sort, right? I have the good pivot. I have the bad pivot, right? I have the time complexity. I have the space complexity for the normal partition algorithm, right? I also have the space complexity for the in-place partition algorithm. Okay, let us quickly draw this table. So time complexity in the good pivot case is order of n log n, right? In the bad pivot case is order of n square. The space complexity in the good pivot case for the normal partition algorithm is order of n log n. For the bad, it is order of n square. If we use an in-place partition algorithm, the good pivot takes order of log n space for the recursion stack, and the bad pivot takes order of n space for the recursion stack. Is this clear? So this is time complexity and this is space complexity. Is this clear, guys? Yes. Jay says, can we get rid of the recursion stack somehow? Can we somehow convert this recursive program into an iterative program, write a while loop and achieve O1 extra space? Well, Jay, it is not possible. For quicksort, it is not possible. Right? For some other algorithms, for some other sorting algorithms, you can do it in a manner that gets rid of the recursion stack. But for quicksort, you need to have the recursion stack manually. Right? So it will take at least order of log n space. Okay. Cool. Yes, then all these notes will be provided to you in the chat. So just join the chat over there. I will upload this PDF over there. Okay, so you all will be able to access it. All right, cool. Now there's a catch though. There is a catch now. So how many of you are aware of this thing called the stability of sort? Stability of sort. Right. So for example, we know that things like bubble sort, right, things like insertion sort, things like selection sort, right, and even merge sort, they can be implemented in a stable manner. They can be implemented in a stable manner. What about quicksort? Is quicksort stable or is quicksort not stable? Right? Is quicksort stable? Quicksort stable. What do you think the answer is? Well, that depends on the partition once again. Right? If we are using this normal partition thing, then yes, it is stable. Right? Because we can totally make sure that we do not change the order. We are creating new memory, so we can totally make sure that we do not change the original order of elements. Okay, so if we are allowed to use extra space, if we are allowed to use n log n space or n square space, then yes, we can implement quicksort in a stable manner. But that is not usually how we implement quicksort. Okay, usually in practice we implement quicksort in this in place manner. Right? We usually optimize on the memory, and we almost always implement quicksort in this in-place manner. And if we implement this in-place algorithm, then it turns out that this in-place algorithm is not stable. Okay, this in-place algorithm is not stable, and there is no way, there is absolutely no way to make quicksort stable unless you are allowed to use extra memory. Okay, if your partition algorithm uses constant memory, then it cannot be stable. Is that clear? So the general answer for is quicksort stable is no. No. Because partitioning in O1 space causes the the stability to break. Okay. Why is it not stable? For that, we will have to analyze the partition algorithm. So, I mean, notice that in the partition algorithm, we are swapping elements. Right? In the partition algorithm, we are swapping elements a lot. Right? So what really happens is, if it could totally be the case that there was a 2 over here and there was a 2 over here, and these 2's get swapped. Right? For integer arrays, it doesn't really make a difference. It doesn't really make a difference, but it makes the sort unstable. Okay, so whenever you have quick sort implemented in an in-place manner, it will always be unstable. And I mean, the basic reason is that we are swapping elements, and that is causing the instability. Everything clear till now? Yes, no? Cool. So this was basically quick sort. Now let us quickly talk about the last thing that a lot of you have been asking for. How do you select? How do you select a pivot? Right? So till now we have realized that the complexity of quicksort, both the space and time complexity, will depend on how we choose the pivot. So how can we choose a pivot? Right? That's the question. So normally what we do is we either choose any pivot, right? Any pivot, like the 0th element or the last element. Okay, this is a bad way of choosing a pivot. This is a bad way of choosing a pivot. Alternatively, what we can do is we can choose a random pivot. Okay, so what does a random pivot mean? Instead of always choosing the 0th element, or instead of always choosing the last element, or instead of always choosing the middle element, right? We choose random element, right? We take a random number generator and we generate a random number from 1 to n, and whatever that number is, we will choose that element as the pivot. Okay, and the third case is choosing a pivot intelligently. So maybe choosing a number, choosing an element which is guaranteed to split the array into half. Right? So what sort of element is guaranteed to split the array into half? If we choose the median of the array, right? If we choose the median of the array, then we are guaranteed that half of the elements will be smaller and half of the elements will be larger. Yes? Does that make sense? So these are 3 of the several strategies that we use to choose a particular pivot. Okay. Now let us quickly see. For this particular strategy, in the worst case, it can remain order of n square. Okay. In the best case, or in average case, on an average, right, it will be order of n log n. Okay, because we are not doing anything, right? We are choosing pivot. We're choosing the 0th element as the pivot. Okay, we are not doing anything intelligent over here. For this particular case, also it is going to be exactly the same. Worst case is order of n square. Average case is order of n log n. Okay. For this median case, now we are choosing the pivot intelligently. So in this case, the worst case will be order of n log n, because it is guaranteed that our pivot is always the middle element, and the average case is also order of n log n. Is this clear? First of all, is this clear? That for both these cases, the worst case can be order of n square, but if we choose the median of the array, then the worst case is order of n log n. So then it becomes much more efficient. All right. Is that clear? So even if you choose a random pivot, your complexity can be order of n square. All right. So if these two cases are exactly the same, then what is the difference between these two? Can someone tell me the difference between these two? Can someone tell me the difference between these two? Choosing a random pivot versus choosing the first element as the pivot? Well, that just makes sure. So the time complexity wise, right? Time or space complexity wise, choosing a random pivot, right? Random pivot, or choosing the first element. This is exactly the same, right? The difference it creates is in dependence on the input. Okay, dependence on the input. All right, so let me give you an example. Why this is important. Suppose that you are Google, right? Suppose that you are Google and you have a particular API. You have a particular service that you're providing to your customers. Okay, what did that service do? So this service looks something like this. So there's a particular URL. There's a particular URL that Google has. Okay, what you can do is you can make a post request with some array. Right? You can have a bunch of arrays and you can make a post request to this particular URL. And what will happen is this API will give back the sorted array. All right, this API will give back the sorted array. This is what Google is doing, for example. All right, let us suppose that. Now, what will happen is, if I am a bad person, if I want to attack Google, right? If I want to attack Google, I will always call this API with a sorted array. Right? I will always call this API with a sorted array because I know that if I choose the first element or the last element or the middle element, the first element or the last element as pivot, if I choose the first element or the last element as pivot, then if I have a sorted array, quicksort will take order of n square time. Right? I know that. So what can happen is some attacker can choose an input which forces your API to take longer, which forces the sorting algorithm to take longer. All right. On the other hand, if Google uses a random pivot, then I, as the attacker, have no way of forcing it to take n square time every time. Right? It could still happen that I happen to give it an input which takes n square time, but I can't repeat it. Right? I can't repeatedly do that. Sometimes it will take n square time. Most of the times it will take n log n time. So I can't attack Google servers now. Does that make sense? So by randomizing the pivot, we are removing the dependence on input. All right. If you choose the first element itself, then it is dependent on the input, whether the array is sorted or it is not sorted. Okay. With random pivot, we are no longer dependent on the input. The worst case and the average case are exactly the same. The time complexity does not change. The dependence on the input changes. All right. Cool. Now, what about this median algorithm? This median algorithm seems to be the best, right? This median algorithm seems to be the best. And it turns out that, in fact, if you have an array, you can find the median of the array in order of n time also. Okay, you can actually find the median of an array in order of n time, right? Very surprising, but that is true, right? And if you do that, then the complexity turns out to be actually order of n log n, right? However, even though asymptotically this is good, in practice, the associated constants are very high. Okay, so selecting the median of an array uses a lot of extra space. It uses a lot of extra things as well, right? You have to do a lot of different calculations. Asymptotically, it is better, but practically it is not cache efficient. It has a lot of different things which makes it practically not good, right? The associated constants, the multiplicative constants are very high. So we usually do not choose the median of the array, right? We usually choose a random pivot. Does that make sense? Yes, Meghna, yes, that is correct. Choosing the pivot would create dependence. However, since we are choosing the pivot intelligently, right? In this case, we are choosing the pivot intelligently, that dependence doesn't really matter because we are guaranteed to split the array into half. Right? We are guaranteed to split the array into half. So nobody can attack us. Right? We are guaranteed that we'll get an n log n complexity. Okay. So the input dependence does not matter in the median case because we are choosing the median intelligently. Is that clear, guys? Cool. So this was all about quicksort. So just to recap, we discussed what quicksort was, right? We discussed this pen and caps problem in which you could not really compare elements. You could only compare pens with caps and you could only compare caps with pens. But we saw that using quicksort, we can still sort them, right? We can still match them up, right? We saw the time complexity of quicksort. We saw the space complexity of quicksort. We saw that partition can be in place or partition can use extra memory. If partition uses extra memory, then it will be stable. If partition is in place, then it will not be stable. Okay. And we saw that, okay, there is something called normal quicksort. There is something called randomized quicksort. Randomized quicksort chooses the pivot randomly, and that makes it so that the dependence on input is removed. Okay. You can also choose median as the pivot, but that has high associated constants. So we don't really do that. Is that clear? In practice, whenever you see a quicksort implementation, it will almost always have a random quicksort implementation. Right? It will almost always choose a random element as a pivot. Right? Because practically that is what performs best. Asymptotically, it is not the best, but practically it performs the best. All right. Cool. So this was today's lecture. We are done with today's lecture. All right. And what I want everyone to do is, first of all, there is a link in the video description. Right? Link in the video description. There's a link for the practice set. Practice set. Right? There will be 4 questions, I think, in this practice set. Please make sure that you go and attempt them, because if you do not actually code these things yourself, you will forget it. All right? Please actually code these things yourself. The second thing is that there's a link to a chat discussion. Right? If you go in this chat, you will be able to find everyone who is in this YouTube thing. You will also be able to contact with other students who are currently studying at Scale. Right? You will also be able to contact different instructors who are working at Scale. Right? So I will also be present in this chat and discussion, and we will be able to help you live. So please go ahead and participate in this chat to clear your doubts. If you have any further doubts, if you want to ask something extra, then please participate in this chat. Whatever I have done in this lecture, the PDF notes will also be shared in this chat discussion. Okay? This PDF note also will be available in this chat description. And finally, I mean, we will be live every single day. We will continue with this series for at least a couple more months, right? So it will be really good if you can subscribe and hit the bell icon so that you will be notified of the video every day. Right? We are going to have a class every day at 6:30 p.m. 6:30 p.m. to 7:30 p.m. Right? Today it got a little extended. Today it is already 8 p.m. now. Sorry about that, but usually the class will be 1 hour. Okay? And this assignment will be open forever. Right? So I remember for the first assignment, it happened that the assignment got closed after 1 day, but that is not the case. This is a practice set, so this will be open forever. So even if you are watching this video later on, even if you're not watching this live, if you go to this practice set, you will be able to take these problems. You will be able to attempt. All right, then. That was it for today. See you in next class and see you in the chat. Let's hope that all of you do the practice set, and let us see you in the discussion, and see you tomorrow. All right, then. Bye-bye, guys. Have a nice day.